Today we want to start off with a few homework problems. The first one up is just kind of a mechanical question about linear transformations. We're given a linear transformation and we're told what this linear transformation does to the standard basis for R2. It says that t of 1, 0 is 2, 5, and t of 0, 1 is negative 1, 6. So what we're asked to do is find t of 5, negative 3. So since we know what t does to 1, 0 and 0, 1, I can write 5, negative 3 as a linear combination of the vectors e1 and e2. So this is going to be t of 5 times e1 minus 3 times 0, 1. This is why 1, 0 and 0, 1 is the standard basis for R2, because it's really easy to write everything in R2 as a linear combination of those two vectors. So we should make a note of that. E1 and E2 is the standard basis for R2. Everything in R2 can be written as a linear combination of E1 and E2, and that linear combination is unique. Pivot in every row, pivot in every column. Pivot in every row means everything in R2 is a combination of those vectors. Pivot in every column means that is a unique linear combination. So there's only one way to write 5, negative 3 as a combination of these two vectors. 5 times the first one minus 3 times the second one. Since t is linear, I can do this next step. So this is going to be 5 times t of 1, 0 minus 3 times t of 0, 1. So the reason that we can go from this second step to this third step is since t is linear. That's why we get to do that. This is important. Anytime we come up with some proof in linear algebra, and we're given a linear transformation, this is what we're going to want to do with it. We're going to want to remember that linear transformations respect linear combinations, and this is probably why we need the transformation to be linear, because we're going to take the image of a combination and make that the same combination of the images. So we know that the image of 1, 0 is 2, 5. So this is going to be 5 times 2, 5 minus 3 times negative 1, 6. So it's going to be 5 times 2 is 10, plus 3 is 13, and then 25 minus 18 is 7. So the first step in this problem is to find the image of a particular vector. And then the second part is to find the image of x1, x2, some generic vector x in R2. So if we want to find the image of x1, x2, we do the same thing. Write x1, x2 as a linear combination of our standard basis vectors. It's x1 times 1, 0 plus x2 times 0, 1. Use the fact that t is a linear transformation, and we'll respect this linear combination. Now we'll use the given information, what the linear transformation, the image of the standard basis vectors under the linear transformation, and drop in the images. So it's going to be x1 times 2, 5 plus x2 times negative 1, 6. And then we can put these together into one vector. So it's going to be 2x1 minus x2, 5x1 plus 6x2. If we plug x1 is 5 and x2 is negative 3, then we come up with 13 and 7, which is what we had before. So we could have saved the second problem, or the first problem for second, done the second problem first, and then had a formula for doing the first problem. But coming up with 13.7 was not the point. Recognizing that given a linear transformation, that linear transformation will respect your linear combinations. A quick DVD bonus material moment. This is the end of the problem for as far as section 1.8 goes. But 1.9 is about finding the standard matrix of the transformation. We know that if a transformation is linear, then there is a matrix that implements the map. And since T maps R2 to R2, there's a 2 by 2 matrix that implements the map. So if we note, we can write this vector 2x1 minus x2, 5x1 plus 6x2 as a matrix times the vector x1, x2. So this is the matrix 2, 5, negative 1, 6 times x1, x2. So I have 2x1 minus x2, 5x1 plus 6x2. And so that 2, negative 1, 5, 6 is the standard matrix of the transformation. So that's the standard matrix of the transformation. When we say the standard matrix of the transformation, we mean the matrix of the transformation relative to the standard basis. So in that way, everything ties to that matrix stuff that we were doing at the beginning. Furthermore, notice that this transformation from R2 to R2 is an injective and surjective transformation because this matrix 2, 5, negative 1, 6 is row equivalent to the identity matrix. So this matrix is invertible. So I forgot which direction I was going. Was I doing invertible matrix or 1-to-1 and onto? The transformation is 1-to-1 because there's a pivot in every column, and it's onto because there's a pivot in every row. And it's also an invertible transformation because the standard matrix of the transformation is invertible. All right, so the other problems are about transformations that aren't linear transformations. So in 24, we're told that an affine transformation, I'm not sure how to pronounce that, it's a word that I've only ever read. So we have a transformation T maps Rn to Rm. Has the form T of x equals ax plus b. So A is an m by n matrix plus some b in Rm. So if it was just T of x equals ax, then we have a linear transformation. But the question is, what happens if we make an affine transformation and add b? What if we write it in the form mx plus b? So A is an m by n matrix, and B is an Rm.
Yeah. Yeah.
All right. We want to show that T is not a linear transformation if B is not 0. So our goal is to show that T is not a linear transformation if B is not 0. All right. So here's what we're going to use. We know that if T is a linear transformation, T respects linear combinations. So here is one of the things that we have to, if B is equal to 0, then T is a linear transformation. That's what makes a linear transformation. We get a linear transformation if it can be represented with matrix multiplication. But we do not have, but if B is not 0, then T is not a linear transformation. So here's one of the things that we can use. If T is linear, then T of 0 is equal to 0. If T is linear, then T of 0 has to equal 0. This is because T represents, T respects linear transformations. The way that we want to use this is, so if T is linear, then T of 0 is equal to 0. This is not an if and only if, but I want to use the negation in the other direction. So if T of 0 is not 0, then T is not linear. So if we change the order and negate the statements, then that's equivalent. If A, then B means if not B, then not A. So the first statement has the form A implies B. So the second statement says not B implies not A, which I think is called the contrapositive, but I'm never sure. I should probably be more confident in things like that, but I'm also not very good at arithmetic, so there you go. So what the easiest way to show that affine affine, I don't know. It's the easiest way to show that T is not linear if B is not 0 is to show that the image of the 0 vector is going to be equal to B. So that's what I want to use. So T of 0, oops, I spelled T wrong, is A times 0 plus B. A times 0 is for sure 0. So if B is not 0, then T of 0 is not 0, and T is not linear. One thing that we should note here is that we can use this T of 0 equals 0 business to show that something is not linear. We can't use it to show something is linear. Just because T of 0 equals 0 does not mean that T is linear. This is very similar to when we talk about convergence way back in Calc 2. In a series, if the limit of the terms of a series is not 0, then the series diverges. But we can't just turn that around and say if the limit of the terms is 0, the series converges, because that's false. We know that that's not true. That's why we had all those friggin' tests for convergence. But we can say if the series converges, then the limit of the terms must be 0. That's the only thing that we do get out of that. So we're using kind of the same structure. If A then B means that not B implies not A. So in 25, note that X is a linear combination of the vectors P and V. So the image of X is going to be a linear combination of the image of P and T times the image of V. So that's what we want to use in 25. Just going to make a quick note. So X has the form P plus TV. And since T is linear, this is equal to T of P plus little t times T of V. That's once again, since T is linear. So the image is either this line, T of P, line through the point T of P in the direction of T of V, or it gets to just a point, which we refer to in this problem as a degenerate line. And that would be the case where T of V is equal to 0. So the idea here in both of these problems is that a linear transformation respects linear combinations. All right, let's pause the video here and come back and talk about subspaces.